Hello everyone, this is my second video on YouTube and it will be a problem on Leetcode and it's a daily question of course. It's about finding the largest value in each tree of row. So here there is an example to understand well the problem, which means for each level of the tree we have to find the maximum and add it to a certain array. So here it will be our output array. And for example, here we have three levels on our tree. For the first level, we have only one node is the root, so it will be the maximum, of course. So we add it in our array. So here there is our one. And on the second level, there is two nodes. So we take the maximum, we take three, we add it. And for the third level, of course, we have three nodes and we take nine and add it. And at the end, we have to return our array. Um, so I think this is not that hard. Of course, this is a medium problem. So yeah. And here we have to make a breadth a breadth first search, so it will be easy. A BFS. If you don't know what is a BFS, you can take a look on this website. I recommend it. It's uh, it's the best website for data structures to understand well what they are doing with schema, and there is a lot here. Yeah, so for example here our tree, if we do a BFS and for each iteration we have to print the value of the node, it will be like this: 1, then 2, 3, then 4, then 5. So it will be by levels. So here the idea is to travel this by a BFS, but we have to make something to mm, yes, we have to create something such that we know in which level we are. So for example here, if we are at 1, it will be 1 for the level, for example. And for the 3 and 2, it will be 2 for our parameter. So it means we can compare these nodes together, but we don't have to compare them with the 1 because they don't have the same level. And same thing here for 9, 3, and 5. Um, so how we can do it? I mean, this is the class of our tree. So this is the, you can say it's like a struct on C language. So we have left and right. This is the constructor with the value, and this is a constructor with value and left and right. I think the best idea to do what I said, to track the levels, we have to create another class such that in our class we will have the node and the level. So let's begin. Say for example we will have class, let's say, how can I name it? I don't know. How can you call it? Class node level. Okay. So we will have our tree node, and we will have our level. We'll define a constructor. So node level, it will take the node, of course, and the level. So this node equal node, this level equal level. So we will use this, and the idea here is to, for example, here we will have, of course, a queue. So why we will use a queue? Because it will be a BFS. So in our queue we have to enqueue the one, and when we dequeue it, we have to enqueue his child. So the 3 and the 2. And now when we dequeue, we have to save this value of node level. An instance of this will be saved. So when we have to dequeue, for example, 3, we have to check if they have the same level for the value we dequeued in first. So if they have the same value at level, we can compare them and we take the maximum. But if they don't have the same value at level, it means that we ended for the first level. I mean, don't know if you understand it well, but we can code it and I'll try to explain to you. So I think we can use the queue. Yeah, I don't know if it exists. Queue in Java. Yeah, this is a queue interface in Java. Yeah, this is in French, so turn off. Yes, we have the add, we have the remove, we have the peek. So here they use the linked list for the queue. Yeah, I think it works perfectly. So we can use this for our queue, and this will be a queue of the node level class I defined. So now there is another problem, is how to know the levels we are doing the queue. I think we can create a variable e, we can increment for each iteration. Yes, for example, if we enqueue, so the root will be always 1. So this is an information we already know. So we can put for the level directly 1 for the root, and for the others, every time we dequeue something, we have to check the level, and after that, when we enqueue his child, we have to increment the value of the level. Yes. So let's begin with our queue. So how we define it? We can say queue node level queue equal new linked list, of course, of node level. Yeah, so this we don't need it. So we have to know that it has the add method and the remove method that we will use. So we will begin with the root. So we already know that we have to put the root at the first. So q that add our root. And now we have to do something. Of course here, not root, sorry. It will be new node level that takes the root and the level of 1. Okay, yeah. Now we will loop until the queue becomes empty. So while I think there is queue is empty. So while now queue is empty. It means while the queue is not empty, you have to do something. Mm, yeah. Mm, it means we can't only dequeue and add in the child and doing that. Yeah, there is something we have to know it because I mean we have to know where we are, on which level we are. So of course we have to make a variable about the maximum. It will be 3 node max. We will call it max. It will be root first, and we have the list. Of course, we have to create our list. Integer output. I will call it output. Call new. Let's take it as the array list. Integer. Now we know that our root is in our queue, but when we dequeue, we have to check something. So, so we dequeue, we add 1, we unqueue his child with 2, or I should say, we have to check the peak before we dequeue. So here, when we change this, it won't be a tree node, it will be node level. So because we will need the value of the level on which we are. So here I'll take this, create it here, node level. How can I name it? I would say it will be max. So here we have to add the max. No, max, I used it. Max level, max level. Because we will need to use this. And here we will not use tree node. We don't want this. So we have our one in our queue. We have to check something for the queue. I think we can check. Yeah, I think I find the idea here. Idea is to make this max level as null in the beginning, and we check if this is null, we have to dequeue, and we have to enqueue the childs, of course. Let's try it now. So here it will be this. So if max level is null, max level equal our queue dot remove. So this will give us the one, and we have to add the one, of course. So output dot add max level dot node dot this is val, yes, dot val. Now we have to enqueue the childs, of course. So queue dot add of new node level root. No, it won't be root. Sorry, it will be max level dot node dot left, and here the second parameter will be max level dot level plus one. Yeah, we can copy this and make it here. That's right. Oh, sorry. We have to check, of course, if the left and the right are not null, because if it is null, it will be a problem. So before adding them to a queue, we have to check if this is not null. So if max level dot node dot left is different null, so we will do this. And same thing here about the right. Yeah, it's right and left. And this is when the max level is null. So now, what if max level is not null? Like in this, when we are doing this. Um, Now, if it is not null, what we will do? Now it means that we have 3 and 2 after we are doing all this. We have 3 and 2 in our queue. And of course with levels 2. Um, I think we will need another variable. So yes, we will need another variable of node level, of course. Node level. We call it TMP. As first. Else, so here, if our max level is not null, so we have to peek on our queue, and we have to check if the level of our peak in our queue is the same as our level in max value. So if they are the same, we have to dequeue in this variable and compare them, compare between this variable and max level, and we take the maximum, of course. If they are not the same, we can set our max level, sorry, directly by the value of this. This means by the value of the peak. But here also it will be another problem. So I think we will have to add this after we check if the value of the peak and the max are the same. So we will not add 1 here, but after we are checking if the 1 and 3 has the same levels. If they have not the same levels, it means that we we finished with the level 1, so we can add our maximum. Let's do it here. So yes, check q dot peak. Yes, it will give us the peak. So if q dot peak dot level equal, or I will start from this if they are not equal, max level dot level. So we will add the max level value, and we can of course dequeue into the max level. Level equal q dot remove. And we can I think add it directly to with TMP, so let's say TMP max level, of course. We can do this. So why I'm doing this? Uh, just to write less code. So I mean here also I can do TMP equal max level, and at the end of the loop I will check if I can add the childs or not in the TMP. Q dot remove TMP equal max level. Yes, all this I can write it at the end of the loop. And here I would say TMP, 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 TMP. I think this is better. And now if they are equal, so it means they are equal. Now if they are equal, I have to dequeue in TMP and take the max between TMP and our max level. So TMP equal max, no, sorry, Q dot remove. And now I will check the values. So if TMP dot node dot value is greater than max level dot node dot val, so I have to say that max level is equal to TMP. Yeah, I think that's it. So we have to return our our output at the end. Return output and batch write. Oh, yeah, why I don't have the 9? Oh yeah. Yes, because at the end, the queue is empty, but we didn't add the last value of the last level, because here in our loop we are adding the maximum after we are on another level of the maximum. So it means here for the 1 we are adding 1 after we are beginning with the level 2. But for the level 3 we don't have level 4. It means we don't add the level 3 on our array, so we have to add it here. So output that add max level dot node dot value. So this will work. Yeah. Yes, I think that's it. You can submit. Oh, oh my god. This is an error where not read field left because it's null. So I'm doing something here. Hmm. Oh yeah, I think I have to check here. Because here the input is an empty tree. I don't have anything, so I just return it if root no, just return new linked list. Or yeah, check it here. Do this if root null, just return output. So it will be an empty array, of course. Add this case, check if it works. No. Okay, so that's it, guys. We'll check the complexity. It's linear, so we are good, I think. So that's it, guys. I hope you understand something, and sorry for my English. And I will say to you to another video. So have a good day and bye bye.